Hello, everyone. This is our part 4 on climate change. In this lecture, we'll be able to talk about the carbon isotope and how it helps as a proxy to detect the climate of the period, of that specific period. For example, let's say Cretaceous or to Triassic time, Jurassic time. Anyway, so same thing as we did with the oxygen isotope, carbon isotope also it has the two main isotope we have is C12 and C13. If we look at this C12 in the molecule of CO2, carbon dioxide, we have C12O2 and C13O2. This is again uh, carbon 12, carbon 13. The difference is the number of neutrons. This one has six, this one has seven. They have six protons because they are carbon both, but this one has six neutrons, this one has seven neutrons. The mass here is about 12. 6 plus 6 is 12, and his 6 plus 7 is 13. Again, here we have, if you compare, for example, a sample, if it has, you have here C13, here C12, and this sample right here, we have more of the green dots, which means more of C13 compared to the standard. We say that this sample has a heavy uh, delta 13C. But if you have more of C12, we say that the delta 13C is depleted, is very low. So either it can be higher if you have more of C13, which is heavy, or lighter if you have more of C12. So if you remember, we talked about oxygen isotope O16, O18, and we see that O16 evaporate easily because it's lighter. For carbon 12 and carbon 13, we're going to talk rather about photosynthesis. And so what happened here is that the plant takes C12 because organisms prefer C12 in their photosynthesis. And again, here we have the explanation of why plants prefer the lighter isotope. So the plant take C12 to make their food, and this is the reaction right here. Six molecule of CO2 with carbon 12 isotope plus water in the presence of light from sun. We got sugar, and you can see here that C12 right here removed from the atmosphere is incorporated into sugar. Of course, the plants release oxygen as a byproduct. So what does this mean? It means that the plants, they become rich in C12. Why? Because they prefer to remove C12 from the air right here rather than C13. So because they take C12 a lot, they become rich in C12. And so these are living things either in the ocean, because in the ocean also we have phytoplanktons, we have plants. They take C12 in their to make their food, their sugar. And when they die, when they get buried, the C12 is removed from the atmosphere. So C12 right here is removed from the air and incorporated into this phytoplanktons. And this long-term storage is called carbon sequestration, means that the plants remove CO2 from the air, which is good because if you remove CO2 from the air, you're going to reduce the greenhouse gas, which cause the reduction of the temperature. Less CO2 in the atmosphere, less greenhouse effect, climate will be cooling. But beside the fact that the plants remove CO2 from the air, remember that the plants, what they store here, they store this C12. This applies to this phytoplanktons in the ocean, but also it applies to coal formation. Again, here we have the trees, they remove C12 from the air and they incorporate that into their tissue right here. And finally, when they get buried, they become rich in C12. This is an explanation again. So in terms of plants, we remove CO2. And which isotope is removed? C12. Again, because the plants prefer C12 than C13. When these plants die, they get buried, and finally they form coal. And that coal happen to have high C12. So if you look at the ratio here, because this C12 increase here, the whole ratio becomes lower. Same thing, photosynthetic microorganism in the ocean, they also take CO2 with C12 isotope. They remove it. They prefer the C12. And so because these living things here, they remove CO2 with light carbon isotope, this C13 would be concentrated, would be higher. So remember, anytime you remove C12 from the ocean, you end up having more of C13 in the water. It increases. So because you have a loss of CO3 with 13 isotope carbon, the shell would incorporate this CO2 with isotope 13 in their shell. Why C13? Because this C12 here is removed by the plants, by the microorganisms. You remove C12 from the water, you end up having more of C13. This C13 here will be incorporated um, into the shell fragments. So, by the way, the shell, they don't take the CO2 in the shell, but rather, let me write down here, rather CO3 2 minus. It's a long story. We're going to talk about this later on, but this shells, they take CO3 2 minus into their shell. But that C here is the heavy one. The bottom line here is that it's not actually CO2 actually. It's rather CO3 2 minus. But C13 here will be also C13 here. So while the plants take CO2 with the light carbon, the shell, they take CO3 with the heavy isotope. And so because here we have more of C13, because we have more of this means this would be higher also. So higher C13 means higher ratio. Very simple. Okay. So the plants that take this CO2 here with light isotope, when they die, they move to the bottom and they form what we call black shell. So black shell, they will have high C12. Okay. This means that the ratio C13 of C12, because they have a loss of C12, the ratio will be lower. Okay. So let's recapitulate one more time here. In the air, in the plants right here, they remove C12, CO2 with C12 isotope because it's preferred, it's light. These trees, they become rich in C12, they get buried, and the coal itself will be rich in C12, which means when C12 increases, the whole ratio decreases. Same thing for black shell, but this one is in the water. So this plant right here takes CO2 with the light carbon isotope. They get buried. When they get buried, this black shell retain more C12, and more C12 means lower ratio. The living thing, the shell, however, because we have C12 is removed, we end up having more of C13 in the water. And because you have more of C13 in the water, they incorporate this C13 in the shell, which causes C13 to increase and the ratio also to increase. So the bottom line is that the shell will have high ratio and the biomass will have a lower ratio. And you can read this to explain exactly what happened. Okay? So this is for what happened to the isotopes C12 and C13, both in the plants, in the land, also in the ocean, and also the ratio of this isotope in the shell. So again, this is exactly the explanation of what I talked about. So when the organic matter is removed, so let's say, for example, black shell or coal is buried, they will be rich in C12, which means when you have high C12 right here, the ratio will become lower. So this ratio that is lower in the ocean, I mean, in these plants means that probably let me write this down here. So again, C12 is high in black shell and in coal. This means that the ratio C13 over C12 will be higher. I'm sorry. I'm sorry. C12 is higher. This means the ratio is lower. Okay, so this bottom number here, this C12 in the bottom increase, this means the ratio will decrease. And that's what you have in black shell. So the C12 increase right here in the black shell because the anchor price is 12, because sort of increase, the ratio decreases. So anytime you see a lower ratio or delta C that is lower, it means we have a burial of C12. It removed from the ocean, I mean from the atmosphere, and it get buried underground. So the bottom line is that the organic matter is rich in C12, which means it has lower delta C13. How about if this black shell is used? Like remember, black shell has fossil fuels like oil and petroleum. Coal also we use it for energy. If that coal or black shell is used, like burned fossil fuels, for example, when you burn fossil fuels coming from black shell, what do? You're gonna release C12. If you release C12, actually it's CO2 here. If you release this, a loss of C12 in the air, what happened is that C12 will increase in the air, which means that C13 over C12 will decrease in the air. And that's what you have here. Release of C12 rich carbon source decreases C13 exactly because this delta 13 is proportional to this delta 13C. If you release carbon, I mean, if you burn the fossil fuels that have a loss of C12, remember C12 is incorporated into the plants right here. If you release this in the air, this will increase. This means the whole ratio will decrease. Okay? And if you release, of course, CO2 in the air, that will cause global warming because CO2 is a greenhouse effect. And that's a perfect example of Paleocene, Eocene thermal maximum because at the time we have a loss of release of um especially methane that has a loss of C12 and that causes a loss of greenhouse effect. Okay, so let's clear this out and move to. So here is an example of how to calculate delta 13C. Same thing as we did for oxygen isotope, same thing, same equation, except that here we have delta 13C equals ratio 13C over 12C for the sample minus this ratio of the standard. The standard case is Vienna P D bilmenite, VPDP. It's like a bilmenite is a fossil that is used as a reference. For oxygen, we use main ocean water. For the carbon, we use this bilmenite, which is a fossil, and the standard is called VPDP. Okay, so now let's look at how we calculate this delta 13C. Same thing as we did for oxygen. Here's an example for organic rich rock, coal. So we have the ratio in coal sample. This is the value. For the standard for VPDB is this ratio right here. How to calculate delta 13C? First, use the equation, which is right here. A ratio of the sample minus ratio of the standard divided ratio of the standard times 1000. And when you plug the numbers, you get minus 37.1. What does it mean? If you have very low delta, I'm sorry, this is should be 13 here. Let me just correct this. Should be 13. So what does it mean by delta C equals negative 37? Let's look at the next slide to see the explanation. So what does it mean by delta 13C equals negative 37? So remember, we're talking about organic rock coal right here. Why coal has such delta C that is negative? It's very simple. Again, if you look here, the plants, the coal come from the plants. And the plants, they take this CO2 into there to make photosynthesis. So when they get buried, they become coal. Now, coal is rich in C12. Now, if you look at the ratio 13C over 12C, because this increase, we have a loss of C12 in the coal, the ratio as a whole will decrease, will become very low. And that's what you got here. Very low value means we have a loss of C12. Okay? So very depleted delta C13, which means very, very low ratio, means high input of organic carbon, which means rich in C12. So anytime we have very, very low delta C, it means simply we have a loss of C12. If you have a loss of C12, meaning that we have the ratio that is very low. Okay? So that's what it means. Depleted delta C13 simply means you have a loss of this C12 right here. So buried organic matter like plant biomass, it will carry with it this C12 into it. So you have more C12 here in coal. And this means delta C13 will be lower. Again, if you look at the ratio, remember, when this ratio is higher in the plant in the coal, this means the whole ratio is low. So we say it's depleted. When organic carbon is buried, C12 is removed from the carbon cycle and the atmosphere. You remove this from the air. And remember, when you remove this from the air, you have less CO2, and less CO2 means less warming. In other words, we have cooling, possible cooling, because it's a contributor. So, climate implication, cooling phase. This is the best example for Carboniferous period. Remember, during the Carboniferous period, right before the Triassic time, we have a loss of trees. You have forests of huge amount of trees, and that's why it's called Carboniferous period, because these trees they get buried and they form carbon. I mean, coal, which is made of carbon. So imagine you have a lots of trees. This tree they will remove CO2 extensively. This means CO2 would be decreased. This means the temperature would be dropped. Why? Because less greenhouse gas, less temperature. Okay. In fact, during this Carboniferous period, we have barrier of coal, and barrier of coal removes CO2 from the air, causing the temperature to be cooler because the CO2 was reduced, was removed by the trees. Okay. All right. So, example of calculation of another example. Organic rich rock black shale. Again, we have delta the ratio in black shale sample. Remember the last one we did coal right here. Remember, this is coal from plants in land, like in tropical forest, for example. And this time we're gonna do black shale that formed from planktons in the sea. When this plankton die, they move to the bottom, they get buried, they form what we call black shale, and this black shale is where we get our oil or petroleum or hydrocarbons. So let's look at this example number two. So black shale has this value, right? 0.10900. The age of black shale, let's say it's 94 million years ago. Imagine you find that the rock is 94 million years ago, which is Cenomanian-Turonian boundary. It's like you say Jurassic period. This is Cenomanian-Turonian boundary, which is Cretaceous time. The standard is 0.12372. They ask you to calculate delta 13C. Again, formula, I write the formula right here. Substitute with the value. So we have this number here, put it here. The standard put it here and here times the 1000 and you get minus 30.10 per mil. How do you explain this? I remember we're talking about black shell. Black shell, they come from this planktons right here. So how do you explain this very negative number? What happens simply is that this living things right here, these plants especially, called phytoplanktons, they take CO2 from the water. And what type of CO2 they take? What kind of carbon isotope they take? The one that is light, C12. They take it away, they form their food, sugar, and once they die, they get buried. When they get buried, they take this C12 with them into here. So they become rich and rich in C12. At the same time, C13 would be enriched in the ocean and also in the atmosphere. Why? Because simply this CO2 is removed not only from the water, because that CO2 also here will be diffused into the water and it will be taken away by the plants. When the plants take it away, these plants they will be rich in C12. And if you remember, when C12 increase, the ratio decrease. And that's why delta 13C will become lower because you have a loss of C12. Okay? So black shell, we have low delta C13 simply because this they have a loss of C12, more C12, lower ratio. Interpretation here still deplete in delta 13C, which means you have very low delta 13C, which means there is an organic matter input. Anytime delta 13C is very, very low, this means there's organic matter. Okay? Black shell forms under low oxygen conditions, preserving organic matter. So C12 get buried right here, and this means C12 is drawn down all the way to the bottom and it gets stuck in there. It gets sequestered in there. And if you remove CO2 from the water, and also remember from the air, because this water, this CO2 here will be diffused into the water and will be taken away by the plants. The plants will be rich in C12 and move down to the bottom. And this process causes a reduction in CO2 in the air, which will trigger cooling. And because this is 94 million, this is likely linked to Cretaceous oceanic anoxic event, which means there is a time when you have very low amount of oxygen in the bottom, which cause this black shell to be preserved, organic matter in them to be preserved because you have low oxygen. So again, this number right you got here means we have depleted organic matter or depleted the 13C, which means you have more C12, which may have lower value, more lower ratio, lower delta 13C, which means you have the input of organic matter. How about this now? Carbonate shell with high delta 13C. So you have your sample, we have your value in this carbonate shell. We have the standard and the ask you to calculate delta 13, same thing. Substitute the numbers and you get plus 10. What this plus 10 means? How can you interpret this positive 13C? Definitely it means this. It means that if I try to write here, so again, if you go back to R, one best way to understand this, go to the R ratio, for example, 13C divided by 12C. So positive 10 means that this is increasing. This means delta, this ratio is increasing, means what? Means that this 13C is increasing. So how do you explain? So this is linked to the fact that this ratio is increasing, which means this 13C is increasing. How is that possible for shell to have a higher 13C? Let's see here. Now we know that the planktons, they will remove C12. Why? Because they prefer carbon 12. They get buried and they get black shell. So if you remove C12, remember also we have here 13. Let me write another color here. Remember here also we have 13 CO2. If you keep removing C12, you end up having more of C13, which makes sense. You remove this, you end up having more of this. And this C13, not necessarily C2, CO2, it's actually should be CO3 2 minus. It's a long story. This is the one that is incorporated into the shell. And because we have a loss of this C13, why again? Because C12 is removed by the plants. You remove C12 by the plants, you end up having more C13, and shell will end up having more C13. As a result, the ratio will be higher and delta C will be higher. So phytoplanktons remove C12 right here. Surface water will be enriched in C13, meaning that when this is removed by the plants, this C13 will be enriched in the water. So marine organisms right here, they will incorporate this C13 enriched seawater, which is this one here. Not necessarily CO2, it should be CO3 2 minus. It will be enriched in C13, will be incorporated by the shell. This means we have high C13 over C12, which means high delta 13C, which means that's how we got this higher value. And this indicate what? This indicate cooling or high primary productivity. Because when you have high positive value for this one here in the shell, which means someone is removing CO2 from the air, and which is the plants. So this indicate either high primary productivity, which means loss of black shell, and also it can also mean cooling because anytime living things, plants remove CO2, we end up having more C13 in the water, which would be incorporated into the shell. So high value of delta 13 in the shell means that we have something that take this CO12, which is the plants, which means you have more productivity, more biomass. And if you remove CO2, it also means we have what we call cooling trend. Okay. Another example, you guys here, shell with low delta 13C methane release. You have your shell carbonate, the age 56 million, the standard is this, so just substitute the numbers and you're going to get this number right here, minus 21.1. Again, imagine that the age of this rock here that we analyze is 56 million. If we try to make sense of these values right here, minus 21.1, shell with very low value of delta 13C, what does this mean? Okay, what you have here, we have methane released into the water and also into the air. This methane right here, which has C12, okay, this methane rich in C12 would be changed into CO2, same thing C12, C12 by oxidation. You don't need to know this in depth, but the bottom line is that this water here is rich in C12, and that C12 will be incorporated into shell. And that shell will end up having higher C13 over C12. Why? Because you have higher C12, and because you have higher C12 into the shell, we end up having it should be here lower value here. As a matter of fact, there's a mistake here. So again, the release of methane, which have a loss of C12, it become oxidized to become CO2, C12. This will be incorporated by the shell. So this means you have more loss of C12, which means C12 will increase and the ratio will decrease. So this should be low, not high. So delta C13 minus 21.1 reflects input of C12, a rich carbon. Anytime we have very low number here, it means you have a loss of C12 in the material, for example, in this case shell. And this is likely from methane, CH4, which is released from the hydrate stable, a hydrate, which is like methane trapped in ice. Okay? Methane has usually values that are minus 60 per mil, and it drives ocean and atmospheric delta 13C down when released. Okay, I know this is a little complicated example, but of course, when you're asked, you'll not be able to get this kind of questions where you have to do this kind of interpretation. The question would be very, very simple, like calculation of delta 13C, for example, and that would be it. So no more complication here. So to put this in context, to understand this low delta 13 with methane release, we have to invoke this volcanic activity. So during this age, 56 million years, what happened is that we have volcanic activity. It's called volcanism, North Atlantic Igneous Provence, that happened between 60.5 to 54.5 million years ago. And that volcano released a loss of CO2. CO2 is a greenhouse effect. It causes temperature to go higher. And because temperature goes higher, the this hydrate that has a loss of methane is released right here. And because this methane is released into the water, but also into the air, what happens to this methane? Two things. Either it will be incorporated by shell, or or uh, or basically it will cause the CH4 release in the air will cause the temperature to go up because CH4 is greenhouse gas. Or the CH4 in the air can be oxidized to become CO2. CO2 will be diffused into the water. That diffusion will cause this water to be rich in C12, which will be incorporated into shell, and shell will be having more C12. I know it's a little complicated, but don't worry about the type of question you're going to have in this. I'm not going to ask you about oxidation or any complication like this. The question will be simple. But anyway, you can see that how scientists interpret the results. We have your delta C negative 21. This means it's very depleted in um, in carbon 13, which means that shell must have very gonna write down here delta 13C low negative 21.1 means that we have this ratio right here 12C. That's how if you'd like to understand this thing here. If this means this is down. This means the bottom one here is high because when this goes down, this means high. C12 is high. And now we need to know where this C12 rich carbon come from. That's where you have to look at this diagram here. This rich C12 rich water comes from the fact that methane is released, and methane has low 12 isotope oxygen, carbon oxygen, and this carbon oxygen here will be transferred, become CO2, C12. This will be incorporated into the shell. And because you have a loss of C12 here, and that's what because you have a loss of C12 here in the shell, where does C12 come from? It comes from CH4, which could turn into CO2, and CO2 will be incorporated. This carbon-rich water will be incorporated um, into shell. So you have a loss of C12 here, which means if you go backward, means that the ratio is lower, means delta C is lower. That's how it works. So again, we have volcanism. This is a loop here. Volcanism causes more CO2. More CO2 causes global warming. And global warming causes ocean warming also. And ocean warming causes methane hydrate release. This get released. It will release it with thaw. It will melt. And this will release CH4. CH4 will be oxidized to CO2, and this will be taken by the shell. So more CO2, especially the one that has 12 here. And this means that the water will be C12 rich. And this will cause C13C to drop. which means also more warming. And again, if you put this in context, this negative 21.1 means that we have this warming right here that take place. Why? Because CO2 is released by volcano, and also emission of CH4, which causes warming in the air. And you can see it here. It's called Paleocene Eocene thermal maximum right here, and that's caused by both the volcanic eruption that release CO2, also sometimes CH4, but also the fact that this hydrate, they melt and they release CH4. The release of CH4 will cause high temperature. Okay, so you can see here two scenarios right here um, of climate change. We have carbon first time, where we have that take from 359 to 219 million years ago. And we have global cooling. Why global cooling? And that's what you should remember again. If you don't understand what's the past, what happened before those diagrams, which are a little complicated, you try to understand the link between um, photosynthesis, for example, that remove light carbon with the climate. For example, here we have widespread forests. And because you have a loss of forest, you have a loss of photosynthesis. Okay? And we know that the plants, they prefer C12. So CO2 with C12 would be removed. If C12 is removed, first, removing CO2 in general will cause cooling. And that's what you have here. So organic matter, carbon is removed from the cycle, which means we have global cooling. That's number one, because you remove CO2. And this plant right here will be rich in C12. And what this means, if this plant right here is rich in C12, I gotta do it one more time, C12, if this is high in the trees, this means that the ratio, if this is high, the ratio is low, meaning delta 13C is low. And that's what you have here, delta C13 decreasing. I mean, no, it must be, yeah, in the atmosphere, yeah, I'm sorry. For the plants, we have a loss of C12, which means in the plants right here, delta 13C will decrease. Okay. And because you remove in the air, in the atmosphere, you're going to remove C12. So C12 in the atmosphere will decrease. So this means this value here, C12 decrease, which means the whole thing here increase. So delta C13 increase, I'm talking about here about the atmosphere. Okay. So going back to the climate, if you have less CO2, we have global cooling. Okay. So again, we can see that we have an increase in delta C13 in the atmosphere. And however, C12 would be rich in the trees. However, PETM, the volcanism that we talked about before, 56 million years, what happened is that because of volcanism, it will release CO2. CO2 is a greenhouse effect. It causes the temperature to warm up, and the warming itself causes thaws or permafrost that stabilize the hydrate. Once permafrost is melted, the methane hydrate beneath them will start to release CH4, which is rich in C12. So because of the release of this methane that has a loss of C12, the atmosphere will be rich in C12. As a result, delta 13C will drop sharply in the air and also the water. So the increased greenhouse gases, that's the climate feedback. When you have more CO2, and to make it simple in the diagram here, volcanoes release CO2. CO2 causes temperature to go higher. This high temperature causes the melting of the marine hydrate. The marine hydrate will release CH4. CH4 also will be converted to CO2, which also causes higher temperature. Or also CH4 itself will cause the temperature to go high. You can go like this. And this high temperature will cause the melting of more hydrate, and the melting of hydrate will cause more CH4, and more CH4 will cause more temperature will cause more hydrate, and so on and so on. So this is a loop. It's called positive loop. Anyway, okay, let's see here what we have. Now, we talked about isotopes. It's a little complicated, I know, but again, the question you'd be able to have would be very, very simple, very straightforward, no complication whatsoever. Very, very simple. I know the carbon isotope, especially, it's a little complicated. But if you know how to calculate delta 13C and with the with understand how the plants remove C12 because slide, they end up having more C12, that would be more than enough. Anyway, beside oxygen isotope that will help us understand the climate, past climate, we have also growth rings. The space of the tree rings record a history of the temperature and precipitation during the tree lifetime. More growth happen in warm, wet years, producing wider growth rings. So anytime we have wider rings like here, for example, it's wet, but once you have narrow, small rings, it means it's dry. So here we have three types of trees. We have living tree, we have dead tree, we have buried tree. The buried tree is the one that will give us an old, this is the buried ring right here. We have rings, and you can see the rings here from the center all the way up. And this ring here corresponds to different period, wet for wider and narrow for dry. And we have the same thing for the dead tree. Same, we have rings here. And what we do, we correlate the dead tree with the buried tree right here. And so this goes with this. And because the dead tree continue here with the rings all the way to here, we compare that dead tree with the living one. And you can see that this part here correlates with this one. And so you can continue. And at the end, we compile all these rings and we compile one whole composite tree ring record from the buried tree, from dead tree, and from a tree, and you end up having all these records right here. And you can tell exactly what happened during this time of the life of all these trees right here. Last part is pollen. Pollen also can give you an idea about the climate. For example, grass pollen dominate in warm temperature. Right here, for example, this is warm temperature, as opposed to spruce pollen, which dominate at a cooler time. And if you can look at this cool right here, you can see time that are colder, warm, cold, warm, and so on and so on. So you'd be able to find also this kind of historical record of the temperature using pollen. Thank you.